You ever stop and think about what actually fuels our world? You know, the high-energy stuff we rely on every day? Well, it turns out there's this one single family of molecules behind, well, a whole lot of it.
I mean, they're the core of gasoline, right? The stuff that's propelling millions and millions of cars every single day.
They're also what flows into our homes as natural gas, keeping us warm when it's freezing outside. And get this, on a way deeper level, their simple little structures are basically the scaffolding for the incredibly complex molecules that make life itself possible.
So what are these master molecules? They're alkanes, and today we're going to break down exactly what they are and why they're so fundamental to, well, pretty much everything.
All right, so to really get alkanes, we've got to start with the absolute star of the show, the element carbon.
See, carbon is the foundation of a whole field of science called organic chemistry. And an organic compound, that's just a fancy way of saying it's a molecule with carbon in it. It's literally the chemistry of life.
So what's carbon's superpower? It's all about the number 4. That's right, 4. A single carbon atom can form 4 super strong, stable bonds. And this is the magic key because it lets them link up with other carbon atoms, creating these long chains and crazy complex structures that are the backbone for millions of different molecules.
Okay, so now let's zoom in a bit. When you have a molecule that's made of only carbon and hydrogen, nothing else, we call that a hydrocarbon. They're the simplest organic compounds you can get, but don't let that fool you. As we've already seen, they pack a serious punch.
And inside that big world of hydrocarbons, there's one family that is the most basic, the most fundamental of them all, the alkanes. Seriously, you can just think of them as the original Lego bricks of organic chemistry.
So what makes an alkane an alkane? The key word is saturated. Now, all that means is that it's holding on to as many hydrogen atoms as it possibly can. Every single bond between its carbon atoms is a single bond. No double bonds, no triple bonds allowed. They're just full, stable, and happy.
Let's meet the first couple members of the family. You've got methane, 1 carbon, that's the main ingredient in natural gas. Then, you link 2 carbons together, fill it up with hydrogens, and boom, you've got ethane. These are the absolute simplest building blocks of the whole family. And what's so cool is that there's this really elegant logic to how they're built. You can figure out the formula for any straight-chain alkane with one simple rule: CnH2n plus 2. So, if you tell me you have 5 carbons, I know you've got to have 12 hydrogens. It's this beautiful, simple pattern that builds the whole family.
But remember that whole 4 bonds thing? Well, it doesn't just mean carbon makes long, boring, straight chains. Oh no, it gets way more creative than that.
And this leads us to a really crucial idea called structural isomers. It sounds complicated, but it's not. It just means you can have 2 molecules with the exact same chemical formula, same parts list, right? Same number of carbons, same number of hydrogens. But because you arrange them differently, they end up being completely different things with different properties. Okay, check this out. Both of these molecules have the exact same formula, C4H10. But just look at the difference in their shape. Butane is a straight chain. Methylpropane, it's branched. And that tiny little change in shape has a huge effect. Methylpropane boils at a much lower temperature. It just goes to show you it's not just what you've got, it's how you put it together.
And the variety doesn't even stop there. Besides branching, these carbon atoms can even link up and form closed loops or rings. You get molecules called cycloalkanes, like cyclopropane or cyclohexane. It's just another layer of complexity built from the very same simple blocks.
So, okay, you've got millions of possible chains, branches, rings. How on earth do chemists keep track of it all? It'd be a mess, right? Well, they realized they needed a universal language.
Because without a system, it would be total chaos. And that's why this group, the International Union of Pure and Applied Chemistry, or IUPAC for short, thankfully, created a set of universal rules. And the goal was simple. Any chemist anywhere in the world can look at a structure and know its single official name. No confusion. And it really just boils down to a simple 3-step puzzle. First step, find the longest continuous carbon chain. That gives you the parent name. Step 2, number the carbons in that chain, but you have to start from the end that's closest to a branch. And finally, step 3, you name the branches and use those numbers to say exactly where they are. Simple as that. Okay, let's bring this all back home. We're going to connect these molecular structures back to the real world. Because it turns out one of the most important things about an alkane is just how big it is. So here's the main idea. Longer chains are stickier.
They just have more surface area, so they can attract each other more strongly. So to get these bigger, stickier molecules to break apart and turn into a gas, you have to pump in a lot more heat to overcome those attractions.
And you can see this trend plain as day. Look at methane, just one carbon. It boils at a super cold -162 Celsius. Now just add 4 more carbons to get pentane, and the boiling point skyrockets to 36 degrees. That's a liquid at room temperature. And by the time you get to decane, with 10 carbons, you're all the way up at 174 degrees. The pattern is crystal clear.
And this pattern directly translates into how we use these things in everyday life. Those really short chains, like 1 to 4 carbons, they're gases. Think natural gas or propane for your grill. Then you get to the medium chains, maybe 5 to 18 carbons long. Those are our liquid fuels, gasoline, diesel, jet fuel. And the really, really long chains, they become thick lubricating oils, waxes for candles, and even the tar we use to pave our roads.
So think about it. From a dead simple repeating pattern of just carbon and hydrogen, we get this incredible range of materials that have quite literally built our modern world. And it all started by understanding one simple, fundamental building block. It really makes you wonder, doesn't it? What's the next simple discovery that's going to change everything?